Hello everyone, this is Hogan and this is the Machine Learning with Graphs course. I heard that so many people registered this class and I feel more responsibility and I will do my best for this class and you guys. Okay, let's get started. So this class is about the basics of graph theory. So before we get into the details about machine learning and deep learnings for the graph, we need to know about some basics of graph theory. So don't be afraid. So will be very simple concepts and notions about the graph. So once again, we focus on some advances of deep learning for graph dataset. So this is a part of machine learning methods, but I'm pretty sure that your dataset, even though you deal with the natural language or image processing on computer vision, some of your dataset or you already used the relationship between the data implicitly. So if you understand some important idea about the recent advance, so will be very helpful for your research. So let's get started from the components of a complex system. So we have several basic notions in the complex system, which also called graph or network. We use the terminologies interchangeably. So we will give some the idea about how they are different. So we have components. So they are nodes and vertices. So we often denote the component as this N or the V. So N represent the node, the V represent the vertices. And we also say the number of the vertices. We often represent this information using this one. So you will see this a lot. So in this case, so the red color represents the node, right? So number of vertices is 1, 2, 3, 4, 5, 6, 7, 8, right? So using this notation, we can represent this graph data. What about interactions? So interactions is to represent some communication between the previous components, right? It connects between nodes. It connects between the vertices, right? We say the interaction is links or edges. We often say the E. So similarly, using this notation, we can define the number of edges or number of links in the graph input. So the system-wise, we call this one is a network or graph data. Simple, right? So you may wonder how they are different. So networks or graphs, are they the same or not? So usually network often refers to a real system. So the World Wide Web, social network, and metabolic network. So we refers these real system as network. Meanwhile, the graph is more likely to be mathematical representation of a network. So when you need to define the input from more mathematical perspective, it will be better to say this is a graph data, or otherwise you try to understand the real system or learn the data for your application. So I would recommend to use a network. We try to make this distinction whenever it is proper, but in most cases we will use two terms interchangeably. So even in the scientific paper, even some mathematical paper, some people refers the graph data as network. So we started from this distinction, but eventually you will use this term interchangeably. But just it's good to know, right? So this is the example of the node. So in the previous lecture, we have talked about what could be node and what could be the edges, right? So this is another example. So computer could be node when we have the communication between the computers, right? Using the LAN cable or some serial cable, we send and receive data between the computers, and we can create the edge whenever they have some communication between the computers, right? And this is the actor network. I'm not sure how many of you watched the Godfather movie. So we have several actors, Al Pacino and Marlon Brando and Henry Olva. So I'm not familiar with that as well. So, so they have a relationship like a Godfather between Marlon and Al Pacino, right? So we can represent the type of edge using this natural language. So maybe you can predefine the type of edges like this, right? For example, family or co-worker, something like that, right? These are examples. What about this? So third one is, looks like some protein interaction, right? Could be some organ. So depending on some protein is activated in some portion in the organ, and depending on the type of protein, or I mean different protein, their activation will be different. So each activation could be present in this visualization, and they could be a node, and when they are appeared at the same time, and we can create the edge, right? So from your own definition. So that's why the domain knowledge is really important, right? So it is to represent the real system, right? And you try to understand the actual node and try to predict their future communication, or you may just understand the data itself. So that's why it is important to decide the right representation of the node and edge, right? So fourth example is more mathematical, right? So using the number, the number may represent some identifier or some, I don't know, it depends, right? It is so hard, by the way. Just a second, please. All right. So once again, the choice of the proper network representation is important for your success. In some cases, there is a unique and unambiguous representation. In other cases, the representation by no means unique. So here is an example. So the way we assign the links between a group of individuals will determine the nature of the question we can study. So do you think this is appropriate or not? So maybe we can create an example. So individuals. So we have some group, right? We can create a link. Maybe I feel like it depends the criteria of the groups, right? When this represents the domain knowledge pretty well, it may determine the nature of the question, right? So that's why choosing the proper representation is important. So we will come back this later, and you will learn about the many other ways to represent the node and edge. So we started with the concept of the node and edge in the graph space, right? And by having the deep learning technique, so we can learn another relationship between the node in the latent space, right? In the physical space, in other words, graph space, the edges from the pure observation, right? We need to observe the actual interaction, but they are very sparse, so difficult to observe, difficult to disambiguate the nodes or groups each other. So that's why we try to get their essential information and try to represent the node in the latent space, and we can observe that some similar nodes are placed each other in here. So let's say some nodes are placed in here, so their location in the latent space are very, very close each other, right? Looks like they are grouped, right, compared to this node. But when you see the location in the graph space, it could be something like this. So we try to learn their actual relationship. So in the data space, in the graph space, it's difficult to see they are actually related, but by removing the noise or depending on our target property, we will see that they are actually related in the latent space. So by having this latent space, I mean the representations in the latent space, we can train another classifier to find the decision boundary, and we can have better clusters in the latent space. So let me give you another examples, this one, in the future classes, so you will have many chances to discuss about this advantage. So yeah, don't worry about it. So I would like to say, anyway, it is important to decide your own representation. Particularly when you start with your data from the very raw data, right? Oh, this is raw data, right? We need to construct the graph data, right? This is very difficult. So, okay, so let me come back to this issue later. So, in this example, you may have very different communication between the computers, right? The communication could be from the packet exchange or some direct communication between the users, like chatting, or some I don't know, what would be the example? Some send file or the airdrop, could something like this, some explicit communication, right? So I would like to say we have so many raw data, but we need to decide which one is gonna be node, which one is gonna be edges. So we need to filter out irrelevant information. So please don't use all the information for the edges and nodes. So that is the key. Maybe the ability to choose the proper representation could be the most important in your success. So usually in your grad school study, it is likely to use the existing data set. People already pre-processed and filtered out the noise data. But in the reality, it is gonna be very hard and very noisy. So let's just stop talking about this. All right. So we'll come back anyway. So this is another example. So if you connect individuals that work with each other, so we have professional network, right? It is something like LinkedIn, right? So if you connect those that have a romantic and sexual relationship, so you will have the sexual networks. So this is another example. So if you connect individuals based on their first name, for example, Peter's, is gonna be more difficult in Korea, right? We have many similar first name, right? For example, Jiyoung, or I'm sorry, so I try to use English in this class. I don't know. What would be the example? What is a popular name? In English, maybe the Peter and John, or in Korean, in Jiyoung and Minsu, right? So if you connect individuals based on their first name, you will be exploring what? So I don't know. Maybe we connect individuals based on the family name. It's slightly better. It is like the family network. But yeah, in any case, it is a network, nevertheless, right? Okay, so now we have graph data. So we have some statistics in the graph data. First of all, we can start with the node degree. So node degree represents the number of links which are connected to the node, to another node, I would say. It could include a self link. So here we have some examples. So in the case of the undirected data, so undirected data means in the edge, we don't have directional information. So we don't have source and target information. They are just connected. We don't know the information. So in the case of A, they have just one edge, right? So number of links. Oh yeah, I'm confusing the definition. So yeah, it's the number of links, I would say. The node, to the node, right? They have just one edge, right? What about B? B has 1, 2, 3, 4 edges. Simple, right? Number of links connected to the corresponding node. That is the definition of the node degree. What about the directed case? So we need to consider their direction, and by considering that information, we can define an in degree and out degree concept, right? The total degree is the sum of the in and out degree. So here's an example. In the C, how many edges are coming to the C? We have 2, right? What about C? So how many edges are coming out of the node C? 1, right? But their degree, total degree, is the sum of the in and out degrees. It is gonna be the same as the 3, right? Simple, right? This is the concept of node degree. So we can define their average, right? And we can also compute nth moment, right? And we have standard deviation and distribution, right, for the degree data. So when you say some average degree, so you can provide the degree, the average of all the degrees of the nodes, right? So we have degree information for all nodes in here, and we can compute the average score. Will be same in the nth moment, right? Standard deviation distribution will be also the same. This is example. So average degree, you just compute the mean of the degrees, right? In directed case, you can compute the in-out the degrees, right? You just follow this mathematical notations, right?